B sub beta sigma. It's turned into a red pill podcast. This is brutal. Not yet. It's about to be. Capital K equals 1 over g squared times the determinant where the entries given column. What is up, you guys? Welcome back to my channel. We are going to continue to read from Differential Geometry by Erwin Kreyszig. We are in the middle of chapter 4, which is on the second fundamental form and the Gaussian and mean curvature, which those topics we actually already went over. And so we will be pretty close to finishing chapter 4 in this video. But I'm going to start off today with a segment that I've really come to appreciate, which is reading your guys' comments. So I'm just going to kind of go in order that they came in between last time, which actually the last video that I put up, speaking of being on the second fundamental form and Gaussian and mean curvature, that would probably be the first video in this series, which I would say has been a flop as far as view count, which I'm not mad about. When I look at my analytics, I think the reason is that the video before it, which was on lengths, angles, and areas on surfaces, which the title itself is probably not a big hitter in terms of like the Google SEO of those keywords, but the intro to the video was really good, and then it was pretty tight as far as the editing goes. And so I think the algorithm just ended up pushing out that video for another week and decided not to push out the video on the second fundamental form, which I think is okay because the lengths, angles, and area video has been one of the most viewed videos on my channel so far. So thank you guys for all that. And also super close to 1,000 subscribers. So maybe by the time this comes out, it may have hit 1,000, but really close. And so, yeah, thanks everyone for subscribing. But we're gonna read these comments. So I'm gonna start off strong with, of course, Vanderhagen the Stampede, who says, I just wanted to drop a quick note of appreciation for your dedication to engaging with your viewers' comments, especially when it comes to clarifying concepts in math. As someone navigating mathematics in a non-native language, I really appreciate your attention to addressing various inquiries, including vocabulary challenges. My transitioning from translated materials to English math books hasn't been easy, but your explanations really make a difference in bridging that gap. Also, my last comment questioning the usage of inner product was an attempt to properly organize my vocabulary. Keep up the fantastic work. Your insights are greatly valued. Yeah, well, thank you. Vanderhagen the Stampede, isn't your primary language French? Either way, what I heard of, and I don't know Vanderhagen the Stampede's background, but what I heard of is that if you want to really excel as an academic with like a math PhD nowadays, you should really focus on learning German and or Russian. And correct me if I'm wrong on that one. But yeah, foreign languages and excelling in the world nowadays is a whole other topic in and of itself. But then we have another comment which says, I can't help but suggest that a series on category theory would be fantastic to see in the future, which actually was reiterated. I had something I put up on the community tab, which was like, what is your favorite branch or specialty or topic of math? And there was another comment there which said algebraic geometry, specifically when category theory enters the picture. So I'm not really familiar with category theory, but honestly, I've been hearing a lot about it in the last like month or so, in kind of getting a little deeper in some of the math world, I guess you could say. I don't know anything about category theory. Maybe I should. Okay, and this one here is on the lengths, angles, and area video. The last one, like I said, was on the second fundamental form video, but this one I would say is the viewer comment of the week, which is from Roger7341, and this comment goes as follows. Unfortunately, I'm not a real mathematician and I'm way too old to ever become one. Problem is, I'm trying to teach a robot to do what toddlers learned to do while fiddling and fussing with the drawers and doors in their mom's kitchen. I have a mechanism represented by m independent constraint equations and n greater than m joint variables, so it has a mobility of n minus m dependent variables and n minus m independent variables. Its differential manifold may be represented by n minus m orthonormal vectors tangent to the surface and m orthonormal vectors orthogonal to the surface. The implicit function theorem states that I may express dependent variables as functions of the remaining n minus m independent variables, but it doesn't say which regroupings are better than other regroupings. My clue is looking at the row norms of the orthonormal null space matrix and selecting as independent those variables with the largest row norms, those variables with the highest mobility. I can add the robot's grasp to the mechanism model and move it around and reorient it until its mobility has been maximized. After many hours of fussing and fiddling with handles and knobs on the doors and drawers in Mom's kitchen, the toddlers learned how to pull and push on stuff and which directions worked and didn't work. They learned to navigate differential manifolds before entering kindergarten. If toddlers can learn to do it, robots should too. And I like this because it's an application of, I guess, what you would call differential geometry through engineering. It's a real-world application. And I especially liked the last part, which said, if toddlers can learn to do it, robots should too, which reminded me of my favorite nonfiction book. One of my favorite nonfiction books just in general, but my favorite nonfiction book, which is really outside of my wheelhouse completely, which I actually have on the shelf behind me here. It's this blue one, Becoming Human by Michael Tomasello, which is the culmination of several decades of, you could say, hands-on research with non-human primates. And the gist of Michael Tomasello's research is basically doing comparative developmental psychological experiments between great apes, namely chimpanzees, and humans, so like infants and young children, which the comparison is not always obviously apples to apples, but what I mean is in terms of like the time it takes for one of the great apes to become fully developed cognitively versus a human is quite different, because it only takes a few years, 3 to 4 about, from what I understand, for chimpanzees, let's say, to be cognitively fully developed, whereas at age 3 to 4 in humans, we're obviously nowhere near fully mentally developed. But by age 7 in humans, as it goes in Michael Tomasello's research, which he goes over in the book Becoming Human, that's like a critical age where you should see all of the key tools in order to become a cognitively fully developed human. But in order to draw these kinds of comparisons, there obviously has to be an understanding of chimpanzee cognition, right, in order to make the comparisons. So this is from the very beginning, the background section of Becoming Human, which one of the reasons why I like it, just to kind of go back on that for a little bit, the findings are really compelling, especially when you think of them from like an evolutionary standpoint, because basically chimpanzees are a proxy for the so-called least common ancestor between us and the great apes, which we diverged from in turn over tens and hundreds of millions of years. One of the things that it comes down to is human culture and human cooperation, collaboration, and competition that goes along with that are some of the hallmarks, and there are actual like cognitive predicates for that. But it's all very fascinating because you look at humans who stand apart from the other great apes because we have these massive symbolic faculties of language and mathematics. We have these large cultural institutions like governments and universities, and we obviously have all this technology to show for. Why don't the great apes have anything nearly like that? And, you know, it brings up one of these things I've heard Joe Rogan repeatedly say on these podcasts. He'll quote this one other researcher who I forget, but Joe Rogan will keep on saying, the great apes are in the Stone Age, or they're shown using tools, or I actually saw in the news, for instance, there's like an orangutan who was seen using like a plant as a type of medicine by like using it as like a band-aid or something like that. The problem with all of these instances that are being cited is that they're just one-off, and that other great apes don't really copy and replicate or sustain the usage of these tools in the specific ways that we as humans characteristically do. For example, if there is a tool like an axe or something like that that gets invented, all humans across the board will gradually adopt using that axe, and they don't have to go through the process of inventing an axe in order to use it. They just have to be a part of a culture where axes are produced and they can learn how to use the tool. But in great apes, right, they use these tools, they do these so-called novel things that are reminiscent of how we use tools and stuff like that, but it doesn't carry over into their community and stuff like that. So, there's psychological reasons why that happens in great apes and stuff like that. But anyways, I wanted to read this part from the book, which says, chimpanzees and bonobos spend the better part of their day foraging for food. In this context, they have evolved cognitive skills for understanding the workings of the physical world, which we can go back to the citation for Tomasello and Gauss, published in 1997. You can just go on Google Scholar, and I'm sure you can find what that's referencing. But it says they understand 1, space for finding food, 2, object categories for identifying food, and 3, quantities for maximizing food intake. In other words, chimpanzees and bonobos possess the same core knowledge of the physical world that human infants begin to display early in ontogeny, referred to Spelke 2009. So this goes back to the original comment of the week from Roger 7341, which ended saying, if toddlers can learn to do it, robots should too. And we can go one step further and say that our nearest common relatives in the great apes, which we use in non-human primate research as proxies for our least common ancestor, we could say great apes, chimpanzees and bonobos, they have these same core knowledge, understandings of the physical world. So therefore robots should too. And that's just what I wanted to say with that. Yeah, so I guess in today's reading of the differential geometry book, I'm hopefully going to hit in section 46 here, Gauss's Theorema Egregium, which is Latin for remarkable theorem. And this is cited on the Wikipedia page for Riemannian Manifold, which of course I keep coming back to because Eric Weinstein. But we have in the introduction here, it says, in 1828, Carl Friedrich Gauss proved his Theorema Egregium, remarkable theorem in Latin, as I said, establishing an important property of surfaces. Informally, the theorem says that the curvature of a surface can be determined entirely by measuring distances along paths on the surface. That is, curvature does not depend on how the surface might be embedded in three-dimensional space. Bernard Riemann extended Gauss's theory to higher dimensional spaces called manifolds in a way that also allows distances and angles to be measured and the notion of curvature to be defined, again in a way that is intrinsic to the manifold and not dependent upon its embedding in higher dimensional spaces. So this is again going back to how this particular differential geometry textbook, it shies away, it's like one step short of introducing manifolds formally, but it still touches on Gauss's Theorema Egregium, and it basically introduces all of the mathematical structure that one could then go on to understand manifolds with, if not just by generalizing it a little bit further, but it doesn't actually do so. It doesn't actually go into manifolds. Some would say maybe that that is a criticism or a shortcoming of the Kreyszig Differential Geometry book. I don't know, but nevertheless, we're getting to an important section, as we can see here from the Wikipedia page. But it goes on and says, Albert Einstein used the theory of pseudo-Riemannian manifolds, a generalization of Riemannian manifolds, that is, to develop his general theory of relativity. In particular, his equations for gravitation are constraints on the curvature of space-time. So it really just underlines how meta the development of general relativity was with differential geometry for Einstein, you could say. It was a very meta move by everything with absolute differentiation and, the coordinate systems and, pseudo-Riemannian manifolds here. Anyways, We are now in section 44, flat points, saddle points of higher type. A point capital P of a surface capital S is called a flat point, planar point, or a parabolic umbilic if at capital P all coefficients b sub alpha beta of the second fundamental form vanish. Clearly, this property of capital P is independent of the choice of the coordinates on capital S, as follows immediately from the fact that the quantities b sub alpha beta are the components of a tensor. When classifying the points of a surface, for which refer to sections 40 and 41, where section 40 was on elliptic, parabolic, and hyperbolic points of a surface, and section 41 was on the principal curvature, lines of curvature, and Gaussian and mean curvature, we excluded planar points. We will now consider two simple characteristic examples of these points. Example 1, if we rotate the curve x sub 3 equals x sub 1 to the fourth power, for which refer to figure 53, in the x1, x3 plane about the x3 axis of the Cartesian coordinates in space, we obtain a surface of revolution which has a planar point at x equals 0, 0, 0. We may represent this surface in the form quantity x1 squared plus x2 squared closed quantity squared minus x3 equals 0, or in the parametric form, vector x in terms of u1 and u2 is equal to, entry-wise, u1, then u2, then capital A squared, where capital A is equal to u1 squared plus u2 squared. We find that lowercase g is equal to 1 plus 16 times capital A cubed, and according to 38.8, which is that b sub alpha beta equals 1 over the square root of g times the determinant, where column-wise it is vector x1, then vector x2, and then vector x sub alpha beta, where g refers to the discriminant of the first fundamental form. Then we have that b sub alpha alpha is equal to 1 over the square root of g times the quantity 4 times capital A plus 8 times u alpha squared closed quantity, where alpha can be 1 or 2, and b sub 1, 2 equals 8 times u1 times u2 all over the square root of g. At the point capital P given by u1, u2 equal to 0, 0, which corresponds to the vector x equal to 0, 0, 0, all coefficients b sub alpha beta vanish. That is, capital P is a planar point. At capital P also capital K equals 0, where capital K, I believe, refers to Gaussian curvature or the total curvature, while at any other point b is greater than 0, and therefore also capital K is greater than 0. In that case, the surface lies entirely on one side of the tangent plane at capital P. Let us now consider a planar point at which the tangent plane intersects the surface. We may call such a point a saddle point of higher type. Example 2. While a surface in the neighborhood of any ordinary saddle point, which is not a planar point, refer to section 40, has 2 upward and 2 downward slopes. A so-called monkey saddle has 3 upward and 3 downward slopes, 2 of the latter for the legs of the monkey and 1 for his tail, refer to figure 54. Obviously, at such a saddle point, capital P, the corresponding tangent plane intersects the surface along 3 curves passing through capital P. The surface x3, which is equal to x2 cubed minus 3x1 squared times x2, which is equal to x2 times the quantity x2 minus the square root of 3 times x1 closed quantity times quantity x2 plus the square root of 3 times x1 closed quantity, or in parametric form, the vector x in terms of u1 and u2 is equal to, entry-wise, u1, then u2, then u2 cubed minus 3 times u1 squared times u2. This surface has a monkey saddle in the neighborhood of the saddle point given by the vector x equals 0, 0, 0. We find g sub 1, 1 equals 1 plus 36 times u1 squared times u2 squared, and g1, 2 equals 18 times u1, u2 times the quantity u1 squared minus u2 squared, and g2, 2 is equal to 1 plus 9 times the quantity u1 squared minus u2 squared closed quantity squared, and therefore g in terms of u1 and u2 is equal to 1 plus 9 times the quantity u1 squared plus u2 squared closed quantity squared. Hence, g of 0, 0 is equal to 1. Therefore, according to the relation b sub alpha beta equals 1 over the square root of g times the determinant of x1, x2, and x sub alpha beta, we have that b sub 1, 1 is equal to negative 6u2 over the square root of g, b sub 1, 2 is equal to negative 6u1 over the square root of g, b sub 2, 2 is equal to 6u2 over the square root of g, and thus b is equal to negative 36 over g times the quantity u1 squared plus u2 squared closed quantity. At capital P, given in terms of u1 and u2 by 0, 0, these coefficients vanish. At this point, therefore, also the Gaussian curvature is 0 and the normal sections have a point of inflection. Similarly, we may obtain saddle points of higher kind for which the corresponding tangent plane intersects the surface along 4 or more curves. For instance, the surface x3, which is equal to x1 times x2 times the quantity x1 squared minus x2 squared closed quantity, has at vector x given by 0, 0, 0 a saddle point such that the corresponding tangent plane intersects the surface along 4 curves, referred to figure 55 above. Problem 44.1. Give an example of a surface which has a planar point capital P and lies entirely on one side of the tangent plane capital E at capital P, but has a curve in common with capital E at capital P. Section 45. Formulae of Weingarten and Gauss. We first recall the following fact from the theory of curves. To any point capital P of a curve of class R greater than or equal to 2 at which kappa is non-zero, that is, curvature is non-zero, we have associated the 3 orthogonal unit vectors t, p, and b. Any vector bound at capital P can be represented as a linear combination of those vectors. In particular, if the derivatives t dot, p dot, and b dot exist, they permit such a representation. The corresponding formulae are called the formulae of Frenet. In the theory of surfaces, the situation is similar. At any regular point of a surface capital S given with a vector parametric representation x in terms of u1 and u2, which is of class R greater than or equal to 2, we have the vectors x sub 1, which is equivalent to the partial derivative of the vector x with respect to u1, that is to say partial x partial u1, and similarly for the vector x2 being equivalent to partial x partial u2, and n, for which refer to section 34, which section 34 was on the normal to a surface. The partial derivatives of those vectors with respect to the coordinates u1 and u2 can be represented as a linear combination of those vectors. The corresponding representations are called the formulae of Weingarten and Gauss. Let us derive these basic formulae. N scalar product with n equals 1, we have that n sub alpha scalar product with n equals 0, where alpha can be 1 or 2, and where n sub alpha is equivalent to partial n partial u alpha. Hence the vectors n sub 1 and n sub 2 lie in the tangent plane to the surface capital S. Since this plane is spanned by the vectors x1 and x2, we may set n sub alpha equal to c with a subscript alpha and then a superscript gamma times the vector x sub gamma, where alpha can be 1 or 2. We have to determine the coefficients c sub alpha superscript gamma. If we take the scalar product of both sides and x sub sigma, we find that the scalar product of n alpha with x sigma is equal to c subscript alpha superscript gamma times the scalar product of x sub gamma with x sub sigma, which is equal to c sub alpha superscript gamma times g sub gamma sigma. Using the notation given by the relation b sub alpha beta equals negative x alpha scalar product with n beta, we have that the scalar product of n alpha with x sigma is equal to negative b sub alpha sigma. And using the conjugate relationship of the covariant and contravariant metric tensor given by g sub alpha gamma times g superscript gamma beta equals the Kronecker delta with a subscript alpha and a superscript beta, g sub gamma sigma times g superscript sigma tau is equal to Kronecker delta sub gamma superscript tau. We find that the scalar product of n alpha with x sigma then times g superscript sigma tau is equal to negative b sub alpha sigma times g superscript sigma tau, which is equal to negative b sub alpha superscript tau, which is equal to c sub alpha superscript lambda times g sub lambda sigma times g superscript sigma tau, which is equal to c sub alpha superscript tau. That is, we thus obtain the formulae of Weingarten, namely the vector n sub alpha is equivalent to partial n partial u alpha, which is equal to negative b sub alpha superscript beta times x sub beta, where alpha can be 1 or 2, where b sub alpha superscript beta is equal to g superscript sigma beta times b sub alpha sigma. If in particular the coordinates are chosen so that the coordinate curves are lines of curvature on the surface capital S, then g sub 1, 2 equals b sub 1, 2 is equal to 0, for which refer to 41.6, which again is from Theorem 41.3 on the coordinate curves of any allowable coordinate system on a surface capital S coinciding with the lines of curvature if and only if for this system g sub 1, 2 equals 0 and b sub 1, 2 equals 0 at any point where these coordinates are allowable. And therefore, in consequence of that, the quantities g superscript alpha beta are the components of a contravariant tensor of second order, which is called the contravariant metric tensor, as well as the principal curvatures, Gaussian or total curvature, and mean curvature for when the coordinate curves on a surface capital S are lines of curvature given in terms of the fundamental forms. We have that n sub alpha is equal to negative b sub alpha alpha over g sub alpha alpha, then times x sub alpha, where alpha can be 1 or 2, which critically do not sum with respect to alpha. Or we have that x sub alpha plus capital R sub alpha times n sub alpha is equal to 0, where capital R sub alpha is equal to 1 over kappa sub alpha, and alpha can be 1 or 2. And here, since both alphas are subscripts, then capital R alpha and n alpha is not summed. These relations are known as the Formulae of O Rodrigues. They are characteristic for the lines of curvature. We have thus obtained the following result. Theorem 45.1. For displacement in a principal direction, kappa sub n times dx plus dn is equal to 0. We now consider the partial derivatives x sub alpha beta equals partial squared x partial u alpha partial u beta of the vectors x1 and x2. These derivatives are linear combinations of all three vectors x1, x2, and n, since, in general, x1 and x2 are not unit vectors. We set x sub alpha beta equal to a capital gamma with a subscript alpha beta and then a superscript gamma times x sub gamma plus a sub alpha beta times n, and determine the first coefficients a sub alpha beta, and then the coefficients capital gamma sub alpha beta and then superscript gamma. We take the scalar product of n and both sides of the previous relation for x sub alpha beta. Since x sub gamma scalar product with n equals 0 and x sub alpha beta scalar product with n equals b sub alpha beta, we obtain a sub alpha beta equals b sub alpha beta. In order to determine the coefficients capital gamma sub alpha beta superscript gamma, we take the scalar product of x sub lambda and both sides of the relation for x sub alpha beta previously given. Since the scalar product of x lambda and n equals 0, we find that x sub alpha beta scalar product with x sub lambda equals capital gamma sub alpha beta superscript lowercase gamma times the scalar product of x sub lowercase gamma with x sub lambda, which is equal to capital gamma sub alpha beta with a superscript lowercase gamma times g sub lowercase gamma lambda. Since the scalar product of x sub gamma and x superscript kappa equals a Kronecker delta with a subscript gamma and a superscript kappa, where x superscript kappa equals g superscript rho kappa times x sub rho, for which refer to section 32, which was on vectors in a surface and the contravariant metric tensor, multiplication of the previous relation for x sub alpha beta by x superscript kappa yields capital gamma sub alpha beta superscript kappa equals the scalar product of x sub alpha beta with x superscript kappa, which is equal to the scalar product of x sub alpha beta with x sub lambda, then times g superscript lambda kappa. So far, we have determined all coefficients occurring in the relation for x sub alpha beta given above. We will now represent the coefficients capital gamma sub alpha beta superscript kappa in terms of the components of the metric tensor and their derivatives. Since the scalar products of x sub alpha beta and x lambda, for which referred to above, will occur later, it is advantageous to introduce a special notation. We set capital gamma with a subscript of alpha beta lambda. This is equal to the scalar product of x sub alpha beta with x sub lambda. These quantities are called Christoffel symbols of the first kind. So whenever I come to a capital gamma like that from now on, I'm just going to say Christoffel. Since each of these indices may have the value 1 or 2, we have 2 cubed equals 8 such symbols in the theory of surfaces, namely Christoffel sub 111, Christoffel sub 112, and Christoffel sub 121, etc. The dot product for a Christoffel symbol now takes the form Christoffel sub alpha beta lambda equals g sub lowercase gamma lambda times Christoffel sub alpha beta superscript gamma. And the relation for Christoffel sub alpha beta superscript kappa takes the form Christoffel sub alpha beta superscript kappa equals g superscript lambda kappa times Christoffel sub alpha beta superscript kappa equals g superscript lambda kappa times Christoffel sub alpha beta lambda. The quantities Christoffel sub alpha beta superscript kappa, which occurs as coefficients in the previously given relation for x sub alpha beta, are called Christoffel symbols of the second kind, as per the work of E.B. Christoffel. Go figure. The symbols Christoffel sub alpha beta superscript gamma are of fundamental importance in the theory of surfaces, as we shall see later. The transition from one kind of the symbols to the other can be effected by means of the just given relations. Since x sub alpha beta equals x sub beta alpha, the Christoffel symbols are symmetric with respect to the first two indices, namely Christoffel sub alpha beta lambda is equal to Christoffel sub beta alpha lambda, and Christoffel sub alpha beta superscript kappa is equal to Christoffel sub beta alpha superscript kappa. If we differentiate g sub alpha lambda, which is equivalent to the scalar product of x alpha with x lambda, for which we can refer back to the notation given by the relation x sub alpha scalar product with x sub beta equals g sub alpha beta, with respect to u beta, we obtain partial g sub alpha lambda partial u beta is equal to the scalar product of x sub alpha beta with x sub lambda, then plus the scalar product of x sub alpha with x sub lambda beta. And therefore, in consequence of Christoffel sub alpha beta gamma, which is equal to the scalar product of x sub alpha beta with x sub lambda, the important relations partial g sub alpha lambda partial u beta equal to Christoffel sub alpha beta lambda plus Christoffel sub lambda beta alpha, which we will often use. From this, we have partial g sub lambda beta partial u alpha equals Christoffel sub lambda alpha beta plus Christoffel sub beta alpha lambda, and partial g sub beta alpha partial u lambda equals Christoffel sub beta lambda alpha plus Christoffel sub alpha lambda beta. If we add partial g sub alpha lambda partial u beta and partial g sub lambda beta partial u alpha, and from this sum subtract partial g sub beta alpha partial u lambda, taking into account the symmetry with respect to the first two indices of the Christoffel symbols, we find the following representation of the Christoffel symbols of the first kind in terms of the first partial derivatives of the components of the metric tensor. Christoffel sub alpha beta lambda equals 1/2 times the quantity partial g sub beta lambda partial u alpha plus partial g sub lambda alpha partial u beta minus partial g sub alpha beta partial u lambda. We mentioned that the Christoffel symbols do not form a tensor. Their transformation behavior and further properties will be considered in section 47 on properties of the Christoffel symbols. We sum up the results obtained. The second partial derivatives of the vector function x in terms of u1 and u2 by which a surface can be represented are linear combinations of the vectors x alpha, which is equivalent to partial x partial u alpha, where alpha can be 1 or 2, and n. Then we have x sub alpha beta is equivalent to partial squared x partial u alpha partial u beta, which is equal to Christoffel sub alpha beta superscript gamma times x sub gamma plus b sub alpha beta times n, where alpha can be 1 or 2 and beta can be 1 or 2. These important relations are called the Formulae of Gauss. The coefficients Christoffel sub alpha beta superscript gamma defined above are called Christoffel symbols of the second kind. The Christoffel symbols Christoffel sub alpha beta lambda involved in the above relation are functions of the components of the metric tensor, for which referred to the representation of the Christoffel symbols of the first kind in terms of the first partial derivatives of the components of the metric tensor. So you would have a relation for Christoffel sub alpha beta lambda. We may write the formulae of Gauss in a different manner, as will be seen in section 72, which is on further properties of absolute differentiation. Problem 45.1. Prove that a surface for which at every point all coefficients b sub alpha beta of the second fundamental form vanish is a plane. If b sub alpha beta equals 0, then b sub alpha superscript beta equals b sub alpha gamma times g superscript gamma beta, which is equal to 0, and because of the Formulae of Weingarten, also n sub alpha equals 0 for alpha equals 1 or 2. The normal vector to the surface is constant, which means that the surface is a plane. Section 46. Integrability conditions of the Formulae of Weingarten and Gauss. Curvature tensors. Theorema Egregium. We have noticed that the Formulae of Weingarten and Gauss are the analog of the Formulae of Frenet. It was pointed out in section 20 that if continuous functions kappa equals kappa of s, which is positive, and tau equals tau of s are given, there exists a curve whose arc length is lowercase s and whose curvature and torsion are determined by the functions kappa of s and tau of s. Now the analogous question arises whether, if functions g sub alpha beta in terms of u1 and u2 and b sub alpha beta in terms of u1 and u2 of a sufficiently high class are given, there always exists a surface such that the given functions are the coefficients of the corresponding fundamental forms. That is, we ask whether for any given functions g sub alpha beta of u1 and u2 and b sub alpha beta of u1 and u2 and corresponding Christoffel symbols, the partial differential equations given by the Formulae of Weingarten and the Formulae of Gauss always have solutions. In the case of functions of the class r greater than or equal to 3, the answer to this problem is negative unless certain integrability conditions are satisfied, which we will now derive. We will start from the Formulae of Gauss and shall obtain the Formulae of Mainardi-Codazzi and related relations from which the Theorema Egregium will follow. The Formulae of Weingarten lead also to the integrability conditions which will be given shortly. That is, all of these relations which we will go over shortly constitute all integrability conditions of the Formulae of Weingarten and Gauss. As is shown by means of the theory of partial differential equations, those conditions are also sufficient for the existence of solutions of the Formulae of Weingarten and the Formulae of Gauss, in the small, that is, in a suitable neighborhood of any point of the domain under consideration. Let capital S, given by a vector parametric representation x in terms of u1 and u2, be a surface of class r greater than or equal to 3. We must have that partial x alpha beta partial u lambda is equal to partial x sub alpha lambda partial u beta, where alpha, beta, and lambda can be 1 or 2. Which relations may be written in the form x sub alpha beta lambda equals x sub alpha lambda beta. We determine x sub alpha beta lambda. From the Formulae of Gauss, we obtain that x sub alpha beta lambda is equal to partial Christoffel sub alpha beta superscript kappa partial u lambda times x sub kappa plus Christoffel sub alpha beta superscript kappa times x sub kappa lambda plus partial b sub alpha beta partial u lambda times n plus b sub alpha beta times n lambda. And from this, in consequence of the Formulae of Weingarten and the Formulae of Gauss, x sub alpha beta lambda equals partial Christoffel sub alpha beta superscript kappa partial u lambda times x kappa plus Christoffel sub alpha beta superscript kappa times the quantity Christoffel sub kappa lambda superscript sigma times x sub sigma plus b sub kappa lambda times n closed quantity minus b sub alpha beta times b sub lambda superscript tau times x sub tau plus partial b sub alpha beta partial u lambda times n. If we interchange some terms and change some summation indices, we obtain x sub alpha beta lambda equals the quantity partial lambda sub alpha beta superscript sigma partial u lambda plus Christoffel sub alpha beta superscript kappa times Christoffel sub kappa lambda superscript sigma minus b sub alpha beta times b sub lambda superscript sigma closed quantity times x sub sigma plus quantity Christoffel sub alpha beta superscript rho times b sub rho lambda plus partial b sub alpha beta partial u lambda closed quantity times n. If we interchange beta and lambda, we find that x sub alpha lambda beta equals the quantity partial Christoffel sub alpha lambda superscript sigma partial u beta plus Christoffel sub alpha lambda superscript kappa times Christoffel sub kappa beta superscript sigma minus b sub alpha lambda times b sub beta superscript sigma closed quantity times x sub sigma plus quantity Christoffel sub alpha lambda superscript rho times b sub rho beta plus partial b sub alpha lambda partial u beta closed quantity times n. The vectors x1, x2, and n are linearly independent. In order that the above relation for x sub alpha beta lambda be equal to the relation for x sub alpha lambda beta, that is, x sub alpha beta lambda minus x sub alpha lambda beta equals 0, in this difference the coefficient of each of those three vectors must vanish. This means, in the case of n, that Christoffel sub alpha beta superscript rho times b sub rho lambda minus Christoffel sub alpha lambda superscript rho times b sub rho beta plus partial b sub alpha beta partial u lambda minus partial b sub alpha lambda partial u beta equals 0 must hold. These relations are called the formulae of Mainardi-Codazzi. They already occur implicitly in the famous Disquisitiones of Gauss. Mainardi published relations from which follow the formulae previously given, which are due to Codazzi. The above relation for the formulae of Mainardi-Codazzi means that partial b sub 1 partial u2 minus b sub 1 2 partial u1 minus Christoffel sub 1 2 superscript 1 times b sub 1 1 plus the quantity Christoffel sub 1 1 superscript 1 minus Christoffel sub 1 2 superscript 2 closed quantity times b sub 1 2 plus Christoffel sub 1 1 superscript 1 times b sub 2 2 equals 0, and partial b sub 1 2 partial u2 minus partial b sub 2 2 partial u1 minus Christoffel sub 2 2 superscript 1 times b sub 1 1 plus quantity Christoffel sub 1 2 superscript 1 minus Christoffel sub 2 2 superscript 2 closed quantity times b sub 1 2 plus Christoffel sub 1 2 superscript 2 times b sub 2 2 equals 0. Another form of the formulae of Mainardi-Codazzi will occur in section 72, which again is on further properties of absolute differentiation. Equating to 0 the coefficient of x sub sigma in x sub alpha beta lambda minus x sub alpha lambda beta equals 0 for the above relations of x sub alpha beta lambda and x sub alpha lambda beta respectively, we obtain capital R superscript sigma and then sub alpha lambda beta equals b sub alpha beta times b sub lambda superscript sigma minus b sub alpha lambda times b sub beta sigma. It's turned into a red pill podcast where capital R superscript sigma and then subscript alpha lambda beta equals partial Christoffel sub alpha beta superscript sigma partial u lambda minus partial Christoffel sub alpha lambda superscript sigma partial u beta plus Christoffel sub alpha beta superscript kappa times Christoffel sub kappa lambda superscript sigma minus Christoffel sub alpha lambda superscript kappa times Christoffel sub kappa beta superscript sigma. As can be seen by the previous relation for capital R superscript sigma and then subscript alpha lambda beta, the quantities capital R superscript sigma and then subscript alpha lambda beta are the components of a tensor of fourth order, contravariant of first order, and covariant of third order. This tensor is called the mixed Riemann curvature tensor. The inner product of this tensor and the metric tensor, capital R sub tau alpha lambda beta equals g sub sigma tau times capital R superscript sigma subscript alpha lambda beta, is called the covariant Riemann curvature tensor. It is a covariant tensor of fourth order. The components capital R superscript sigma subscript alpha lambda beta and capital R sub tau alpha lambda beta are also known as Riemann symbols of the first and second kind, respectively. From the relation for the covariant Riemann curvature tensor, we obtain g superscript tau lowercase gamma times capital R sub tau alpha lambda beta equals g superscript tau gamma times g subscript sigma tau times capital R superscript sigma subscript alpha lambda beta, which equals Kronecker delta symbol with a subscript sigma and a superscript gamma times capital R superscript sigma subscript alpha lambda beta. That is, capital R superscript gamma subscript alpha lambda beta equals g superscript tau gamma times capital R sub tau alpha lambda beta. The covariant curvature tensor can be represented in a form similar to the relation for the mixed Riemann curvature tensor. We have that g sub sigma tau times partial with respect to u lambda of Christoffel sub alpha beta superscript sigma equals partial with respect to u lambda of the quantity g sub sigma tau times lambda sub alpha beta superscript sigma closed quantity minus Christoffel sub alpha beta superscript sigma times partial g sub sigma tau partial u lambda, which is then equal to partial with respect to u lambda of Christoffel sub alpha beta tau minus Christoffel sub alpha beta superscript sigma times quantity Christoffel sub sigma lambda tau plus Christoffel tau lambda sigma closed quantity, and g sub sigma tau times partial with respect to u beta of Christoffel sub alpha lambda superscript sigma equals partial with respect to u beta of Christoffel sub alpha lambda tau minus Christoffel sub alpha lambda superscript sigma times quantity Christoffel sub sigma beta tau plus Christoffel sub tau beta sigma closed quantity. Consequently, if we insert the relation for the mixed Riemann curvature tensor into the relation for the covariant Riemann curvature tensor, we obtain capital R sub tau alpha lambda beta equals partial with respect to u lambda of Christoffel sub alpha beta tau minus partial with respect to u beta of Christoffel sub alpha lambda tau plus Christoffel sub alpha lambda with a superscript sigma times Christoffel sub tau beta sigma minus Christoffel sub alpha beta superscript sigma times Christoffel sub tau lambda sigma. From the relation for capital R superscript sigma and then alpha lambda beta and the relation for the covariant Riemann curvature tensor follows capital R sub tau alpha lambda beta equals g sub sigma tau times the quantity b sub alpha beta times b sub lambda superscript sigma minus b sub alpha lambda times b sub beta superscript sigma closed quantity. Hence, capital R sub tau alpha lambda beta equals b sub alpha beta times b sub lambda tau minus b sub alpha lambda times b sub beta tau. As follows from this, the first pair of indices and the second pair can be interchanged without altering the value of the components, namely capital R sub tau alpha lambda beta equals capital R sub lambda beta tau alpha. Furthermore, the covariant curvature tensor is skew symmetric with respect to the last two indices. Capital R sub tau alpha lambda beta equals negative capital R sub tau alpha beta lambda, as well as with respect to the first two indices, that is, capital R sub tau alpha lambda beta equals negative capital R sub alpha tau lambda beta, as follows for the relation for capital R sub tau alpha lambda beta. The curvature tensor has n to the fourth components, where, in the case of two-dimensional Riemannian spaces, that is, in the case of surfaces, n equals 2. In consequence of the skew symmetry, namely that the covariant curvature tensor is skew symmetric with respect to the last two indices and with respect to the first two indices, only those components are different from 0 for which lambda does not equal beta and tau does not equal alpha. Hence, in the case of surfaces, only 4 components are different from 0, namely capital R sub 1212 equals capital R sub 2121, which equals b sub 22 times b sub 11 minus the square of b sub 12, which is equal to b, and capital R sub 2112, which is equal to capital R sub 1221, which is equal to the square of b sub 12 minus b sub 22 times b sub 11, which is equal to negative b. These relations are of fundamental importance. Since the Christoffel symbols depend only on the coefficients g sub alpha beta of the first fundamental form, the same holds for the components of the curvature tensor, and in consequence of these relations also for the discriminant of b, and in consequence of these relations also for the discriminant b of the second fundamental form. In consequence of definition 41.1, we thus obtain the fundamental Theorem 46.1, Theorema Egregium by Gauss. The Gaussian curvature K of a surface is independent of the second fundamental form, but depends only on the coefficients g sub alpha beta of the first fundamental form and their first and second derivatives, that is, K equals R sub 1212 all over lowercase g. The meaning of this important fact will be explained in section 57. In connection with the concepts of bending and isometric mapping. By means of the skew symmetry of the covariant curvature tensor and the relations for the components of the curvature tensor, we obtain the following expressions for the components of the mixed curvature tensor. Capital R superscript 1 and then sub 112 is equal to g superscript 11 times capital R sub 1112 plus G superscript 12 times capital R sub 2112, which is equal to negative G superscript 12 then times B, etc. Hence, in consequence of the quantities G superscript alpha beta, which are the components of a contravariant tensor of second order, which is called the contravariant metric tensor, we have capital R superscript 1 sub 112 equals negative capital R superscript 1 sub 121, which is equal to G sub 12 times B over G. Capital R superscript 1 sub 212 equals negative capital R superscript 1 sub 221, which is equal to G sub 22 times B over G. We also have negative capital R superscript 2 sub 112 is equal to capital R sub 2 sub 121, which is equal to G sub 11 times B over G. And then we have negative capital R superscript 2 sub 212 equals capital R superscript 2 sub 221, which is equal to G sub 12 times B over G. All other components vanish. If in particular the coordinates u1 and u2 are orthogonal, namely G sub 12 equals 0, then capital R superscript 1 sub 212 equals negative capital R superscript 1 sub 221, which is equal to B over G sub 11, and we also have negative capital R superscript 2 sub 112 equals capital R superscript 2 sub 121, which is equal to B over G sub 22. That is, in this case, only 4 components of the mixed curvature tensor are different from 0. The meaning of the curvature tensors will be explained in Chapter 7 in connection with parallel displacement and absolute differentiation. For the symmetry properties of the covariant curvature tensor in general and properties in the case of surfaces in 2D Riemannian space, we see that in the case of surfaces of vanishing curvature, for example, planes, cones, cylinders, all components of the curvature tensor are 0. We will now derive a representation of the Gaussian curvature K in terms of the coefficients of the first fundamental form and Christoffel symbols. Using the notation B sub alpha beta equals the scalar product of negative x sub alpha and n sub beta, and the identity of Lagrange, which is that the dot product of A cross B with C cross D is equal to A dot C times B dot D minus A dot D times B dot C, we find that B is equal to n1.x1 times n2.x2 minus n1.x2 times n2.x1, which is equal to the scalar product of the results from x1 cross x2 and n1 cross n2. Noting the relation for the unit normal vector to a surface capital S at a point capital P given by n equals x1 cross x2 over the magnitude of x1 cross x2, which is equal to x1 cross x2 over the positive square root of g, and the relation for Gaussian curvature K equals kappa 1 times kappa 2, which is equal to b over g, where b is the discriminant of the second fundamental form and g is the discriminant of the first fundamental form. We thus obtain square root of g times capital K equals b over the square root of g, which is equal to the scalar product of n with the result of n1 cross n2. We introduce the unit vector m equal to the cross product of t with n, where t is a unit vector in the tangent plane of the surface. Then the square root of g times capital K is equal to the scalar product of the results from m cross t and n1 cross n2 respectively, which is then equal to m dot n1 times t dot n2 minus m dot n2 times t dot n1. If we differentiate m dot n equals 0 and t dot n equals 0 and m dot m equals 1, we have m dot n alpha equals negative m alpha dot n, and t dot n alpha equals negative t alpha dot n, and m dot m alpha equals 0 for alpha equal to 1 or 2. We may thus write that the square root of g times capital K is equal to m1 dot n times t2 dot n minus m2 dot n times t1 dot n, which is also equal to then m1 dot the quantity t2 dot n times n plus t2 dot m times m closed quantity minus m2 dot the quantity t1 dot n times n plus t1 dot m times m closed quantity, and then this is all equal to then m1 dot t2 minus m2 dot t1. Hence, capital K is equal to 1 over the square root of g times the quantity t dot m1 sub 2 minus t dot m2 sub 1. We now take the particular unit vector m equal to x1 over the square root of g sub 1, 1. Then m sub alpha equals x sub 1 alpha over the square root of g sub 1, 1 plus x sub 1 times 1 over the square root of g sub 1, 1 sub alpha, where alpha can be 1 or 2. Since t equals n cross m, which is equal to n cross x1 over the square root of g sub 1, 1, we thus obtain capital K equals 1 over the square root of g times the quantity t dot x sub 1, 1 over the square root of g sub 1, 1 sub 2 minus the quantity t dot x sub 1, 2 over the square root of g sub 1, 1 closed quantity sub 1. Taking the scalar product of the previously obtained relation for capital K and n cross x1, and noting the relation for the unit normal vector to a surface capital S at a point capital P, we have that the determinant column-wise going n, x1, and then x sub alpha beta is equal to the determinant going column-wise n, x1, and then x2 times Christoffel sub alpha beta, and then superscript 2 is equal to the scalar product of n with n times the square root of g, then times Christoffel sub alpha beta superscript 2. Hence, the determinant where column-wise it goes n and then x1 and then x sub alpha beta is equal to the square root of g times Christoffel sub alpha beta superscript 2. Since t equals n cross m, we thus obtain from the relation for Gaussian curvature in terms of the discriminant of the first fundamental form the following representation. Capital K equals negative 1 over the square root of g times the quantity partial with respect to u1 of quantity square root of g over g sub 1, 1, then times Christoffel sub 1, 2 superscript 2 closed quantity minus partial with respect to u2 of quantity square root of g over g sub 1, 1, then times Christoffel sub 1, 1 superscript 2 close all quantities. By interchanging u1 and u2 in the above proof, we can show that capital K equals 1 over the square root of g times the quantity partial with respect to u1 of quantity square root of g over g sub 2, 2, then times Christoffel sub 2, 2 superscript 1 closed quantity minus partial with respect to u2 the quantity square root of g over g sub 2, 2, then times Christoffel sub 2, 1 superscript 1 close all quantities. If we start from the relation of Gaussian curvature given by capital K equals kappa 1 times kappa 2, which is equal to b over g, and use the relation b sub alpha beta equals 1 over the square root of g times the determinant column-wise x1, x2, and then x sub alpha beta, we have that capital K equals b over g, which is equal to 1 over g squared times the quantity determinant x1, x2, x sub 1, 1, and then times the results of the determinant x1, x2, and then x sub 2, 2. Then the result of multiplying those two determinants is minus the square of the results of the determinant column-wise x1, x2, x sub 1, 2. Carrying out the multiplication and expressing the elements of the resulting determinants in terms of the g sub alpha beta and their first and second derivatives, we obtain another representation of the Gaussian curvature. Capital K equals 1 over g squared times the determinant where the entries given column-wise are g sub 1, 1, g sub 1, 2, and then 1/2 times partial g sub 1, 1 partial u1, and then in the second column g sub 1, 2, and then g sub 2, 2, and then partial g sub 1, 2 partial u1 minus 1/2 times partial g sub 1, 1 partial u2. And then in the third column of this determinant we have partial g sub 1, 2 partial u2 minus 1/2 partial g sub 2, 2 partial u1, and then 1/2 partial g sub 2, 2 partial u2, and then negative 1/2 partial squared g sub 1, 1 partial u2 squared plus partial squared g sub 1, 2 partial u1 partial u2 minus 1/2 partial squared g sub 2, 2 partial u1 squared. This determinant is then minus 1 over g squared times another determinant whose elements are given column-wise by g sub 1, 1, and then g sub 1, 2, and then 1/2 times partial g sub 1, 1 partial u2, and then in the second column g sub 1, 2, and then g sub 2, 2, and then 1/2 times partial g sub 2, 2 partial u1, and then in the third column 1/2 times partial g sub 1 1 partial u2, and then 1/2 partial g sub 2 2 partial u1, and then 0. This representation is sometimes called the equation of Gauss. If the coordinates are orthogonal, we obtain from either of these representations of the equation of Gauss capital K equals -1 over the square root of g sub 1 1 times g sub 2 2, and then times the quantity partial with respect to u1 of the quantity 1 over the square root of g sub 1 1 times then partial square root of g sub 2 2 partial u1 closed quantity plus partial with respect to u2 of the quantity 1 over the square root of g sub 2 2 then times partial square root of g sub 1 1 partial u2 close all quantities. Problem 46.1. Determine the components of the curvature tensors 1 of a surface of revolution whose vector parametric representation is given by x in terms of u1 and u2 as u2 times cosine u1 and then u2 times sine u1 and then h times u2, and 2 of a right conoid whose vector parametric representation is similarly given by u2 times cosine u1 and then u2 times sine u1 and then h times u1, for which referred to section 28, and then 3 of a surface represented in the form implicitly x3 equals capital F of x1 x2, and finally part 4 of the torus given in section 43. In the case of a cylinder of revolution, we have capital R sub 1 2 1 2 equals b, which is equal to 0. Hence all capital R superscript alpha and then subscript beta gamma nu and capital R sub alpha beta gamma nu vanish. Any other surface of revolution can be locally represented in the form x of u1 u2 equals u2 cosine u1 and then u2 sine u1 and then h times u2. Since g sub 1 1 equals u2 squared, g sub 1 2 equals 0, g sub 2 2 equals 1 plus h prime squared, and g equals u2 squared times the quantity 1 plus h prime squared, capital R sub 1 2 1 2 equals b equals u2 times h double prime all over the quantity 1 plus h prime squared, for which refer to problem 40.1. So we obtain from the relations for the non-zero components of the mixed Riemann curvature tensor capital R superscript 1 sub 2 1 2, which is equal to negative capital R superscript 1 sub 2 2 1 is equal to h prime times h double prime all over u2 times the quantity 1 plus h prime squared. We also have that negative capital R superscript 2 sub 1 1 2, which is equal to capital R superscript 2 sub 1 2 1, which is equal to u2 times h double prime all over quantity 1 plus h prime squared closed quantity squared. All other components of the mixed curvature tensor vanish, where primes indicate derivatives with respect to u2. For part 2, using the representation u2 times cosine u1 and then u2 times sine u1 and then h times u1, for which refer to the answer to problem 28.2, we have that g sub 1 1 equals u2 squared plus h prime squared, g sub 1 2 equals 0, g sub 2 2 equals 1, g equals u2 squared plus h prime squared, and then b sub 1 1 equals negative u2 times h double prime all over the square root of g, and then b sub 1 2 equals h prime over the square root of g, and then b sub 2 2 equals 0, and then capital R sub 1 2 1 2 equals b, which is equal to negative h prime squared over g, and therefore capital R superscript 1 sub 2 1 2, which is equal to negative capital R superscript 1 sub 2 2 1, which is equal to negative h prime squared all over the quantity u2 squared plus h prime squared closed quantity squared, and negative capital R superscript 2 sub 1 1 2, which is equal to capital R superscript 2 sub 1 2 1, which is equal to negative h prime squared all over u2 squared plus h prime squared. All other components vanish, where here primes denote derivatives with respect to u1. Part 3. Using the notations capital F sub alpha equals partial capital F partial x alpha and capital F sub alpha beta equals partial squared capital F partial x alpha partial x beta, we obtain g sub 1 1 equals 1 plus capital F with a superscript 2 and then a subscript 1. G sub 1 2 equals capital F sub 1 times capital F sub 2. G sub 2 2 equals 1 plus capital F superscript 2 and then subscript 2. G equals 1 plus capital F superscript 2 subscript 1 plus capital F superscript 2 subscript 2. B sub alpha beta equals capital F sub alpha beta over square root of G. Capital R sub 1, 2, 1, 2 equals B, which is equal to capital F sub 1, 1 times capital F sub 2, 2 minus capital F with a superscript 2 and then a subscript 1, 2, all over 1 plus capital F superscript 2 subscript 1 plus capital F superscript 2 subscript 2. Hence, capital R superscript 1 sub 1, 1, 2, which is equal to negative capital R superscript 1 sub 1, 2, 1 is equal to the fraction with the numerator capital F sub 1 times capital F sub 2 times the quantity capital F sub 1, 1 times capital F sub 2, 2 minus capital F superscript 2 sub 1, 2, closed quantity, over the denominator quantity 1 plus capital F superscript 2 sub 1 plus capital F superscript 2 sub 2 closed quantity squared, etc. Part 4. We have G sub 1, 1 equals the quantity R naught plus R cosine U2 closed quantity squared. G sub 1, 2 equals 0. G sub 2, 2 equals R squared. G equals R squared times the quantity R naught plus R cosine U2 squared. And capital R sub 1, 2, 1, 2 equals B equals R times the quantity R naught plus R times cosine U2 closed quantity times cosine U2, for which see section 43. Consequently, capital R superscript 1 subscript 2, 1, 2, which is equal to negative capital R superscript 1 sub 2, 2, 1, which is equal to R cosine U2 all over R naught plus R cosine U2, and we also have negative capital R superscript 2 sub 1, 1, 2, which is equal to capital R superscript 2 sub 1, 2, 1 is equal to numerator quantity R naught plus R cosine U2 closed quantity times cosine of U2 all over a denominator of R. All other components vanish. And problem 46.2, prove the equation of Gauss. We have capital K equals 1 over G squared times the quantity determinant x1, x2, and then x sub 1, 1 times determinant x1, x2, and then x2, 2. The product of those two determinants multiplied together then is minus the square of the result of the determinant x1, x2, x1, 2. If we carry out the multiplication and use the notation relation scalar product of x sub alpha with x sub beta is equal to g sub alpha beta, we find that the Gaussian curvature capital K is equal to 1 over G squared times the quantity where we have a determinant whose elements column-wise are given by G sub 1, 1 and then G sub 2, 1 and then the scalar product of x1, 1 with x1, and then in the second column we have G sub 1, 2 and then G sub 2, 2 and then the scalar product of x1, 1 with x2. And then in the third column, we have x1 dot x22, and then x2 dot x22, and then x11 dot x22. And then this determinant is then minus a second determinant whose elements are given column-wise by g sub 1, 1, and then g sub 2, 1, and then x12 dot x1. And then in the second column, we have G sub 1, 2, and then G sub 2, 2, and then x12 dot x2. And then in the third column, we have x1 dot x12, and then x2 dot x12, and then x12 dot x12. We have partial G sub alpha beta partial U sigma is equal to x sub alpha sigma dot x beta minus x alpha dot x beta sigma. And thus in particular, 1/2 partial G sub alpha alpha partial U sigma is equal to x sub alpha sigma dot x alpha. From the previous relation for partial G sub alpha beta partial U sigma, it follows that partial squared G sub 1, 2 partial U1 partial U2 is equal to x112 dot x2 plus x11 dot x22 plus x12 dot x12 plus x1 dot x122. From the relation for 1/2 times partial G sub alpha alpha partial U sigma, we obtain 1/2 partial squared G sub 1, 1 partial U2 squared equals x122 dot x1 plus x12 dot x12. Hence, by subtraction, x11 dot x22 minus x12 dot x12 is equal to negative 1/2 partial squared G sub 1, 1 partial U2 squared plus partial squared G sub 1, 2 partial U1 partial U2 minus 1/2 partial squared G sub 2, 2 partial U1 squared. Since the upper left-hand subdeterminants of second order of the two determinants in the relation for capital K just given are equal, we obtain the equation of Gauss by means of combining the relations we just went over. So that's where I'm going to stop today. Thanks for watching. See you guys in the next one. Peace. Say goodbye, little boy. Say goodbye.